Good morning, my dear student. On the behalf of KTM College, Nasik and Department of Chemistry of this college, I am Dr. S.R. Labhade welcomes you to the lecture on hydrodynamic voltammetry. Student, in previous lecture we discussed the instrumentation and working of hydrodynamic voltammetry. We know that in hydrodynamic voltammetry, qualitative as well as quantitative analysis can be performed. In today's lecture, we discuss the different applications of hydrodynamic voltammetry. Applications of hydrodynamic voltammetry. First application is the qualitative and quantitative analysis. Qualitative and quantitative analysis of a electroactive species. Student, similar to polarographic analysis, the result obtained in hydrodynamic voltammetry are in the form of Voltammogram. Voltammogram is a plot of cathodic or anodic current versus applied potential. Similar to polarographic analysis, a step-shape curve is obtained here that shows a maximum limiting current and residual current. Therefore, here the hydrodynamic voltammetry result obtained in Voltammogram, that Voltammogram is utilized for qualitative and quantitative analysis. On the Voltammogram, we can determine the potential at 1/2 of the limiting current. Therefore, potential at 1/2 of the limiting current, that is a half wave potential, that is a potential at which analyte species undergo reduction at working electrode or analyte species undergo oxidation at working electrode. Therefore, here half wave potential is a standard oxidation or reduction potential and will directly identify the species which undergo oxidation or reduction at working electrode. Therefore, in hydrodynamic voltammetry, half wave potential is utilized for identification of the analyte species. Here, when we subtract the residual current from the maximum limiting current, we have the limiting current. And this limiting current in hydrodynamic voltammetry is directly proportional to concentration of analyte that undergo either oxidation or reduction at working electrode. Therefore, when the oxidation takes place, this limiting current is an oxidation current or a anodic current. When reduction takes place, this limiting current is a reduction current or a cathodic current. Therefore, limiting current is directly proportional to concentration of analyte, and that limiting current is proportional to concentration of analyte, and concentration of analyte is determined or it is calculated by using this equation. In this equation, limiting current is equal to 1.55 into N into F into A into D raised to 2 by 3 into mu raised to -1/6 into pi raised to half capital N raised to half into concentration of the analyte species, where in this equation I, that is a potential dependent limiting current which is recorded by using this Voltammogram. N is number of electrons involved in oxidation or reduction process. F is Faraday's constant, that is 96500 Coulomb. D is a convection coefficient. In polarography, it is a diffusion coefficient and it is again measured in square centimeter per second. Mu is a kinetic viscosity of the analyte, and kinetic viscosity is equal to viscosity of the solution upon density of solution. Therefore, here mu is a kinetic viscosity of the analyte solution and N is a rotation rate of the electrode, that is number of revolutions per second, and here C is a concentration of the analyte in millimoles. Now here, this is the equation by which we can determine the concentration of analyte and half-wave potential, that is a parameter by which we can identify the analyte. Both qualitative as well as quantitative analysis is possible in hydrodynamic voltammetry. But in hydrodynamic voltammetry, for determination of analyte concentration, we have to perform two experiments. One experiment is for the standard solution containing same analyte, and second experiment for sample solution containing that analyte. Therefore, here limiting current for standard as well as limiting current for sample are measured under identical condition. Therefore, except concentration of analyte, all other parameters are constant. That means here, similar to polarography, hydrodynamic voltammetry is a comparative method for determination of concentration of analyte. Therefore, here in this case, two measurements are carried out, one for standard and another for sample. Therefore, that is limiting current for sample. Here, when we carry out both measurement under identical experimental condition, therefore all these factors becomes constant. Therefore, here I limiting for sample is equal to constant into concentration of sample. Similarly, limiting current for standard is equal to constant into concentration of standard. Therefore, here by using these two equations, equation 1 and equation 2, we can determine the concentration of sample is equal to limiting current for sample upon limiting current for standard into concentration of standard. And in this fashion, we can determine the concentration of analyte in hydrodynamic voltammetry. That is similar to polarography. Here, hydrodynamic voltammetry is a comparative method, and we can determine this concentration of analyte by comparing its diffusion current with the standard solution. In this way, quantitative analysis as well as qualitative analysis is performed in a hydrodynamic voltammetry. Student, beside this qualitative and quantitative analysis, hydrodynamic voltammetry have very important role in detection and determination of the species that exit from the liquid chromatographic column. That is the voltammetric detector. Voltammetric detector means here this detector detect and determines the concentration of the chemical species as it exit from a liquid chromatographic column. Liquid chromatographic column. This is also called as a flow injection analysis or flow analysis of a fluid. Therefore, here voltammetric detector, this is a most important application of this hydrodynamic voltammetry in liquid chromatography. In liquid chromatography, hydrodynamic voltammetry can be used as a selective detector for identification as well as estimation of the analyte species. We know that every element or every substance that will undergo reduction or oxidation at its own potential value. Therefore, here working electrode is mounted in the path of analyte solution and the potential is adjusted to a value where that analyte is either oxidized or reduced. Where that analyte come in contact with the working electrode, its oxidation or reduction takes place, and when this happens, the proportionally current is measured, and that current is directly proportional to concentration of analyte. That means here it can be used as a selective detector for detection and determination of chemical species as that are exit from the liquid chromatographic column. This is called as flow injection analysis or flow analysis. Now here this arrangement or this detector is like this. In this case there is a small tube whose volume is very small. This small tube, here a working electrode is mounted in this fashion. A working electrode is mounted and here a reference electrode is placed. And here this is the flow of that fluid. This is a liquid chromatographic column from which this liquid is given out in this fashion. Here a counter electrode, here a working electrode is mounted. Therefore, working electrode is mounted in a tube or in a path that flows through which a analyte solution or column effluent is flowing. Here this tube is separated by a porous partition or a thin spacer which have or which consisting of a counter electrode. Therefore, here this is a counter electrode. And in between this working electrode and counter electrode there is a porous partition type material that is called as spacer, S-P-A-C-E-R. This is a salt bridge type working. Therefore, here a electrical contact is made between these. Now all these three electrodes are connected to a potentiostat. Potentiostat means this device that gives the constant potential. Therefore, here this is a connection for saturated calamine electrode, reference electrode. This is a connection for a working electrode, and this is a connection for a counter electrode. Now in this fashion, this hydrodynamic voltammetric detector is constructed, and that is a best or very good detector for detecting the column effluent in liquid chromatography. Therefore, in this case, the working electrode that may be rotating disc electrode or rotating platinum electrode, which is mounted in the tube or in the path of the column effluent. Here, the potential of this working electrode is adjusted to a fixed value by comparing with the potential of the saturated calamine electrode or reference electrode. Therefore, potential is adjusted to a value where that particular analyte undergo oxidation or reduction. When that analyte leaves the column and when it comes in contact with this working electrode, that undergo oxidation, because that is a potential to which electrode is already mounted in the path of that analyte solution, having that potential which is sufficient to reduce or oxidize that analyte. Then when that analyte come in contact with this working electrode, that component, particular component is get reduced, while other does not, because that potential is not reduction potential of other component. Therefore, other component does not interact at working electrode, and only specific component undergo reaction at that working electrode, because that is the potential at which that particular species undergo oxidation or reduction. Therefore, here it can be used as a suitable detector, not suitable, it can be used as a selective detector for determination of analyte species or chemical species from the column effluent of the chromatographic column. Now, second application is voltammetric detector. Similarly, the third application is a ampherostatic sensor. Here, for detection and determination of oxygen. Detection and determination of oxygen. Therefore, here, similar to this electrode, similar to this detector, here we know that oxygen is reducible at potential minus 0.05 volt or minus 0.90 volt. Therefore, the potential of this working electrode is adjusted either 0.05 volt versus saturated carbon electrode or minus 0.9 volt versus saturated carbon electrode, to which that oxygen present in a sample solution is is reduced. Therefore, here this working electrode is kept at this potential or at this potential, and this oxygen will come in contact with this working electrode. It undergo reduction, and that reduction current is directly proportional to concentration of the oxygen present in the analyzed solution or sample solution. By this method, we can determine this concentration of oxygen in blood serum, as well as in seawater, in river water, in drinking water, as well as in other solvent by this method. And therefore, here hydrodynamic voltammetry can be used as a good oxygen sensor. Now here, similar to other species like glucose or a cane sugar, sucrose, that may be oxidized or reduced by means of same electrode system, and here concentration of glucose or sucrose that can be measured by this voltammetric detector, and here it is called as amperostatic sensor for oxygen and glucose and sucrose. Therefore, blood glucose is also determined by same method. Now, next application of this hydrodynamic voltammetry is the detection of endpoint in coulometric titration. We know that coulometry, that is a method of quantitative analysis in which we can measure the quantity of electricity for determination of amount of analyte. Coulometric titration is a secondary type of coulometric method in which analyte is selectively oxidized or reduced by using another auxiliary reagent. And this titration is carried out in a coulometric cell. Similar titration we can perform by using such a type of hydrodynamic cell, hydrodynamic electrolysis cell. And here initially the reagent is generated in a cell, then analyte is added and current is measured at that reduction potential, or current is measured at that oxidation potential. Therefore, here hydrodynamic voltammetry can be used as a detector for detection of endpoint in a coulometric titration. Here same polarographic cell, hydrodynamic voltammetric cell is used for determination of this endpoint. Similar to this, there is another application of this hydrodynamic voltammetry, that is a study of physico-chemical study of reaction. This is related with reversible or irreversible reaction. We know that in a hydrodynamic voltammetry we can oxidize the analyte, we can reduce the analyte. Suppose, for example, we have specific analyte that reacts with another substance and that gives the product. And if we carry out this reaction in a hydrodynamic cell or in a electrolysis cell, and initially if we carry out the oxidation of that particular reaction, and in second stage if we carry out the reduction of that particular reaction, if we observe same oxidation current and same reduction current, then we can say that reaction is reversible. Therefore, the course of reversible reaction that can be studied by a hydrodynamic voltammetry, either by oxidizing that analyte and by reducing that analyte. If oxidation current and reduction current both appears in a same value, that indicates reaction is irreversible. And if reaction undergo oxidation but further reduction is not possible, then we do not have a reduction current. Therefore, here oxidation current is observed but reduction current does not, at that time reaction is irreversible. Therefore, here course of reversible reaction and irreversible reaction that also can be studied by this hydrodynamic voltammetry. Therefore, here student, the hydrodynamic voltammetry can be utilized for qualitative analysis and quantitative analysis of electroactive species. Similarly, most important application is a voltammetric detector, then amphostatic sensor for the oxygen, detection of endpoint in coulometric titration, and to study the course of reaction. Student, with this we complete here the hydrodynamic voltammetry. Now the home assignment for hydrodynamic voltammetry. Number 1, question number 1. What is hydrodynamic voltammetry? Dynamic voltammetry. How does it differs from polarography? Or question may be like this. Differentiate between hydrodynamic voltammetry and polarography with respect to their principle and working. Number 3, give the construction and working of rotating platinum wire electrode and rotating disc electrode. Explain advantages of rotating disc electrode over rotating platinum wire electrode. Again, the next question, number 4, how qualitative and quantitative analysis is done in hydrodynamic voltammetry. Next question is explain application of hydrodynamic voltammetry as a voltammetric detector for liquid chromatography. Similarly, give all applications of hydrodynamic voltammetry in analytical field. And number 7, write the equation that shows shows relationship between limiting current and concentration of analyte. Student, this is all about the principle, instrumentation, working and applications of hydrodynamic voltammetry. Here we complete the hydrodynamic voltammetry. Now it's a time to invite you to my next lecture on stripping voltammetry. Thanks for joining me. Wish you all the best. Keep learning. Happy learning.